So today we are doing part 2 of the fundamental theorem of calculus. And this is the part that you're going to use so much, it's just ridiculous. So what it is saying is you are going to take the antiderivative, let me get the highlighter going. You're going to take the integrand and you will find its antiderivative. And then you will take that antiderivative, you will plug in the top limit, you'll plug in the bottom limit, and you will subtract their values. And let me explain how that makes sense through velocity. If I integrate velocity from time A to time B, I am supposed to get displacement over that time frame. So the integral of velocity is the position function. I plug in my final time, I plug in my initial time, and I am just saying, for you physics people, the final distance minus the initial distance. But we don't get to use the letter D, we have to use S for distance, but that's all it is saying right there. And if I look at the graph of a velocity function, let's just say it's like da 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 da. Here's A and here's B. When I look at this as area, come on. When I look at this as area, where velocity is positive, I am adding all of these velocity times time slivers. And then when I hit my velocity being 0, that's when I change direction and I head in the negative direction and I start backtracking. So I end up subtracting away a little bit of that distance gained. And that's exactly what displacement does. So if I were looking at traveling along a line, this example would be I start somewhere on this line. I have a positive velocity until, and I'll call this C. So that just means I'm moving in the positive direction. I might be speeding up, slowing down, speeding up, as I go along. But I am only moving in a positive direction while that velocity is a positive value. Then when time C happens, that's when I change direction and backtrack. And my displacement is looking at what is my location at my final time minus what is my location at my initial time. Actually, I should, there we go, that makes more sense. So if you understand displacement, does this actually make a lot of sense? For those of you who haven't done physics yet, does this make enough sense? Okay, so that's all you need to know to get going on some examples. Here we go. What you need to know is the differential dx is always going to be written either to the far right or in the numerator to the far right. I'm going to take this example and I'm going to take the dx and put it to the far right instead of being in the numerator so that you can see a little bit better who the integrand is. So you have to separate the differential and figure out who the integrand is. And then that's your focus, is doing the antiderivative of that. Now realize that we don't really do anything with the dx, but without the dx, this wouldn't make any sense. The thing is, when we integrate velocity, we have to multiply velocity by a time increment to get it to be a sort of distance. But when I do the actual antiderivative of the velocity function, I'm using a shortcut. I'm using formulas. And I'm bypassing the need to bother worrying about what that dt even represents. So know that when you're using the formulas, you don't see the action taking place of that differential. But that doesn't minimize its necessity. So the dx is representing, if I were to graph this function, and I'm just going to graph the right half of it, from 3 to 6. So essentially we're finding this area. But the way we're doing it is we're cutting this up into a bunch of pieces. And those pieces we're cutting it up into are rectangles. Each of the areas of the rectangles are a value of that function. So for example, let's say about right here, let's make the x-coordinate like 4.1. That looks like where 4.1 might be approximately. The height of that rectangle is 1 over 4.1. It is plugging 4.1 into that function. And then I'm picking 4.1 because it's a random number. I'm just picking a random number, completely random. And so let's say that temporarily we're looking at that specific x-coordinate. I plug it into the function to get the height. And then I am multiplying by some width. That width is that differential dx. Now, I'm not going to solve this definite integral through this process. It is very time consuming and it requires more formulas than we have right now. Instead of solving it through making a bunch of rectangles and adding all their areas together, I'm going to use the fact that the area and the antiderivative are the same. And I'm going to use the fact that I know the formula for this antiderivative. And I can use this to determine the numerical answer instead of going through a very, very, very painful process of setting up a bunch of sigmas and limits. People try to avoid this. We only solve these thoroughly with polynomials. Imagine how much more difficult it's going to be with other functions. So people actually avoid this at all costs. But by doing that, we lose the meaning of the differential. And we use derivatives. We're actually using derivative formulas to help us solve this definite integral instead of using area. So we're using a shortcut, is what this ultimately comes down to. Now, let's forget this. I'm going to erase it, and let's pretend it doesn't exist. And let's look at what you're actually just plain going to be doing. You're looking at the function 1 over x and asking, who do I take the derivative of? And the result that I get is 1 over x. And what is your answer? Right. Now, technically, I have to be very careful, and it is the natural log of the absolute value of x. I don't have to write absolute values here because it is 3 to 6, but I'm going to put it here for the purpose of just being very, very clear of all that is expected normally. And then I have my plus unknown constant c. Now what I'm going to do is I'm going to tell myself I realize this is the antiderivative of the integrand. I still need to bring the limits in. The lower limit is 3, the upper limit is 6. Now, according to the second part of the fundamental theorem of calculus, I take that antiderivative, I plug in the upper limit minus I plug in the lower limit, and I see what I get. When a definite integral takes place, look at what happens to the unknown constant. What do you notice? Yep. So you're going to see in very quickly that I'm going to stop writing plus c when it is a definite integral, but only when it is a definite integral. Because it ends up being a waste of time. But if you don't see that, it's better that you just write the plus c so that you don't forget it when you do need it. And I get the natural log of 6 minus the natural log of 3, which is a number, and that happens to be the area under that function. So the picture you saw that I drew a moment ago put a bunch of rectangles in. It's the area of that region. Now, I do want to ask you, though, how does this number simplify using log rules? Oh dear. Cox just notified me that I've gone over my data plan. Anyway. So do you remember when you subtract logarithms, what does that, how does that condense? And maybe I just don't see that you wrote it in chat. Yeah, divide. So, oh, okay, I wasn't noticing chat because I was getting distracted. So make sure that you remember these rules. But ultimately, the only thing that is new is you realizing that this is how you need to work with this. Now, I've got a few problems that I think would be good to take a look at. In your homework today, you're going to be evaluating a lot of definite integrals. And you're going to have to remember all of those antiderivative formulas, which you're going to start just calling integration formulas. So do you remember what is the antiderivative formula for an exponential function? And you have to go through those formulas and make sure you have them memorized. The antiderivative of 10 to the x is 10 to the x, good, yes, and then divided by the natural log of that base. When I take the derivative, I get the exponential function times the natural log of the base. But when I integrate, instead of multiplying by the natural log of the base, I divide by the natural log of the base. I'm going to put in a plus c for the sake of it. And then I'm evaluating from 0 to 1. The plus c is going to take itself out. And I end up plugging 1 in minus, what is 10 to the 0 power? And then I can even simplify that a little bit more. And so know that what that just found was the area under the exponential function 10 to the x. I'm just going to draw a real basic rendition from x equals 0 to x equals 1. This is not to scale at all. I just found that area. All right, that's all you have to do. So let's look at the next one. Maybe you recognize what's there. Maybe you don't. You can bring rules in like this constant multiple can actually be taken outside the integral if you like. And by doing that, I tried to emphasize a little bit more the formula you are used to seeing. So the antiderivative of this is inverse tangent. So I wind up getting 4 times inverse tangent of t. And I'm not going to put the plus c this time. And when I don't have a plus something going on, I can draw just a single straight line instead of drawing a square bracket. Just a single straight line and put the lower limit and the upper limit on there. If I don't have any addition going on in there, this is very clear. But you will see people who will write just straight lines like that instead of the square brackets. And then I plug in 1 minus I plug in 0. But now you've got to remember, what are these values? With inverse tangent, this is actually saying or asking, what is the angle when the answer to tangent is 1? And there's no, I could put a plus c, but it's going to subtract itself out. Every time I do plus c, it'll end up being plus c minus plus c. And so I don't bother with it, with the definite integral. When it comes to tangent, I like to say, what angle is it that causes a slope of 1? And then I see the correct answer there, pi over 4. And then this is asking, what is the angle for which the tangent gives an answer of 0? Or what is the angle where the slope is 0? And that would be angle 0. So I end up getting literally the number pi. If that is just amazingly beautiful, it is amazingly beautiful. if I were to graph this function, this function looks like a bit of a, well, it's looks like a bell curve. Its highest value is the 4 because of the multiplication. And I just looked at the area from 0 to 1. But that's all you have to do. All right, another one. I'm going to erase a little bit unless you need me to hold it up a little bit longer. Oh, and I also needed to ask you a question that is important to always ask. What angle range was I allowed to use for tangent? Was it 0 to pi? Or was it negative pi over 2 to positive pi over 2? It was the negative to the positive pi over 2 for inverse tangent. This is something that you should always consider when you are working with an inverse trig function, and that's why pi over 4 was okay, because that's in this angle range, and why 0 was okay, because that's in this angle range. Okay. For number 40, you want to recognize that we don't have a rule for division. And that is not a formula that shows up for any particular function. So what do I need to do before I can begin anti-differentiating that? Right. I've got to distribute the division of my u cubed. That means that I'm going to have a 4 divided by u cubed plus u squared divided by u cubed. And you might see exactly what you're working with and be ready to integrate. But I'm going to write it out. When I prepare to integrate 4 divided by u cubed, I want to realize that I've got to use the power rule. And to see the power rule best, I'm going to rewrite it as 4 times u to the negative 3. The only time I don't use the power rule is if it was just a u to the 1 when it's simplified in the denominator. And what is u squared divided by u cubed? That is the one that is best if we leave it as 1 over u to remind ourselves that this is that one time we are allowed to get natural log out. And the one time that we don't use the power rule. So let's integrate. Add 1 to the negative 3 and divide. And then natural log of u. I don't have to have the absolute values because I'm dealing with 1 to 2. I don't have to put a plus c because it will subtract itself out. And then I'm going to simplify a touch. So I plug in the 2, and that's going to give me negative 1/2 plus natural log 2. And then when I plug the 1 in, I'm going to get negative 2. And what is the natural log of 1? 0. So then I wind up getting negative 1/2 plus natural log of 2 plus 2. So 3/2 plus natural log 2. And then you're done. That's all you're expected to do. Now, the next problem I have set up for you is actually on your homework, so I'm only going to take you a little bit through it. The next one is a piecewise defined function, and I want to make sure you are clear that you are allowed to integrate with either continuity or piecewise continuity. Piecewise continuity means, at best, a jump in the graph. Why is it 4 over negative 2? So I've got my constant multiple of 4, and I'm just bringing that over. Then when I added 1 to negative 3, I got negative 2, and then I had to divide by that new exponent. So I was using the power rule in blue, and in yellow is the constant multiple. Did that make sense? So you've got your constant multiple, and then add 1 to the exponent. So I add 1 to negative 3 to get negative 2, and I divide by that new exponent. Okay. This one, I'm not going to finish it because it is a homework problem, but let me first draw it out because I want you to see what's going on. From negative 2 to 0, we're literally just following a horizontal line of y equals 2. Then when I am between 0 and 2, I'm following an upside down parabola that's moved up 4 units. So I'm trying to draw the right half of an upside down parabola. What I want you to observe is this graph has a discontinuity, but it's a jump discontinuity. If I draw a big giant vertical line where that jump happens, that just shows you how it's going to split this up into 2 sections. You have from negative 2 to 0, you're going to follow this. And you could actually just do area if you wanted. And then from 0 to 2, you're following the function with that vertical line cutting off the area. So when you have a piecewise defined function with maybe a jump discontinuity, or maybe it doesn't have a discontinuity, regardless, you're going to set this up where you integrate for a domain the function of that domain, and then add to that the integral over the next piece of the domain. And for this one, you can either use the new rule we just got, you can use a property of definite integrals that we learned about, you could use area to solve that one. But for this second one, you're definitely going to use the new fundamental theorem of calculus that we just got. And then you would finish that. Now, I want to talk to you also about a way that you can combine the 2 fundamental theorems. So I'm going to go back and remind you of today we looked at this fundamental theorem. Yesterday, we were looking at this fundamental theorem. And this fundamental theorem ultimately comes down to now watch what I'm doing, because I am going to combine what we just learned today with yesterday's first part of this property. Some of you may want to use the technique I'm about to use when you are dealing with derivative of an integral. So what I'm going to do is, so if you look at what this is saying the antiderivative of f is the function g. And this is also saying that I do the integral first, the definite integral, and then I take its derivative. According to today's fundamental theorem of calculus, I find the antiderivative of f, and that gives me g. And then I evaluate that from t equals a to t equals x. Then today's fundamental theorem that we looked at said I plug the x in minus I plug the a in. And now I'm going to think about the fact that I'm going to take the derivative of g with respect to x. And then I want to take a good look at what this actually is. If I plug a constant into a function, I get another number out. This is a constant. So I take the derivative of g of x, and the derivative of the constant is 0, and the derivative of g just takes me right back to what f is. So this is a long route of showing you a little bit more with that first part of the fundamental theorem by combining these two ideas together. I also want to show you a way to do an example where you have to chain rule. Whoop. Close your eyes for a second. I didn't erase. You don't want to see this yet. I'll tell you when I'm done erasing. Don't look, don't look, don't look. Okay, you can look. Forgot to erase the stuff I wrote during period 1. Okay. We are going to look at number 14. We did this problem yesterday, but I want to look at it again through a new lens. We're going to find the derivative of h, so we are going to ddx this integral. According to what I learned today, I take this and I need to find its antiderivative. And I personally find it easiest if I say, hey, let's temporarily call this the derivative of some function. Let's just say this is f prime of t. I find that to be the easiest way to work with it, but you can also find a different way. Actually, that's not t, that's an r. I can't apparently read. So this is the formula for the derivative of some function with variable r. Now, according to today's fundamental theorem of calculus, I find this function's antiderivative, and that is f of r. I am then supposed to evaluate it from r equals 0 to r equals x squared. When I plug the x squared into the r, I get the function f of x squared minus, I plug the 0 in, negative f of 0. I want to realize that when I plug that 0 in, I am getting a constant. So when I take the derivative, it's just going to disappear. But by prepping this the way that I've prepped it, what I have now is a better view of the chain rule. I can see that the mommy function is f, the baby function is x squared, and I need to use the chain rule to take the derivative. The chain rule says, take the derivative of the mommy function, plug the baby in, multiply by its derivative. Then if I go back to right here, I have a formula for f prime. And all I need to do is take that variable in that formula and plug in x squared. And that will give me the square root of 1 plus bleh to the third power. I plug in that x squared, and I have my times 2x. So if you struggled a bit with the chain rule, this can help you to write it out more slowly if it was not making sense yesterday. I'm not sure what that question was referring to. Maybe that was when I did this right here. That wouldn't be considered a proof. If you look in your textbook goes through proofs of these if you want to look at the genuine proofs. What we did before when using both FTC. I'm going to leave it at just your textbook has the proofs. Okay, so now you have a quiz today and I want to prep you for it. So I have ready. Hold on. Close your eyes. Close your eyes, close your eyes, close your eyes. Okay, you can open them. Sorry. I realized that yet again I did not erase. So give me just a second. Erase. Oh my goodness. Oh, that's right. That's why I put it on a don't save so that I could close it, say don't save, and then I can reopen it and all that stuff is gone. Silly me. Forgot about that. And now I just have to find it. Okay, here we go. That was the other one. Finally. All right. let's see, we leave, this class is over. I'm still trying to remember, 10:50, correct? Okay. So at 10:45, I need to make sure to get you started. So let's take a good look. See if you can, well, let's see, I'm debating. I'll give you like 1 minute to read this and see how far you can get through it. And then I'm going to start talking through it. Okay. Now I want to point out that the integrands are f of x, and be careful, this one is 2 times f of x. So you've got to read, biggest issue with these is read them very, very carefully. The limits on the integrals, this first one is 1 to 7, which is in a correct order, shall we say. This next one is 7 to 3. That's actually backward. What you might want to do is, if you notice that something is backward, rewrite it forward with the property that you can negate. And that then is going to, instead of being negative 32, it will be positive 32. And then this one is in the proper order, but I want to use the rule of the constant multiple. Will then come out of the integral and multiply by whatever I get for this. So I'm going to solve this integral through the other two. For me to not mess this up, I need to draw this out on an X number line and look at where the numbers are. I've got a 1, a 7, a 3, and those are my numbers. The integral that goes all the way from 1 to 7 in a forward order is 42. Then either you see this as 7 to 3 going backward, or you negate and force it to go forward. It's your choice how you want to deal with it. And then look at where 1 to 3 is. For myself, I like to set up an equation because I will be less likely to screw up my subtractions that could involve negatives. And, you know, those negatives, they belong in jail for all the grades they steal. So what I'm going to write is that I know the integral from 1 to 7 of this function must be equal to the integral from 1 to 3 plus the integral from 3 to 7. And then I plug my numbers in and treat it like an equation. The 1 to 7 is 42. The 1 to 3 is what I'm trying to find, plus 3 to 7. So 3 to 7 is actually positive 32. And I just realized the way that I wrote that is confusing, because technically this is I should do this. I should leave this as the 7 to 3 is negative 3 to 7. Leave it there. And then if I want to look at what is the integral from 3 to 7, I negate what I have, and that will be 32. I realize that I should have written that as it is still equal to negative 32. And that means the integral from 3 to 7 is 32. But I had that written incorrectly, which is why I prefer to write them all out like this in an equation. So I subtract the 32, I get 10. And then I remember that I have to multiply that by 2 to find out that 20 is the answer to that integral. Okay, let's look at another one. And I am recording this so you can look at it later. This one's a tough one. And okay, I'll walk through it quickly. Okay, let's go a little bit quickly. This is the integral from 0 to x, and it's asking where is g non-negative. Non-negative means positive or 0. I'm going to start with if x is equal to 0, then I am getting the integral from 0 to 0, which means it doesn't really matter what function it is, I'm getting 0. Then I want us to look at if I move forward from 0 to 2, I'm dealing with, I have added positive numbers on. And the entire time that x goes from 0 to 2, I'm continuing to add more from 0. So I am getting only positive answers out as I go from 0 to 2. When I do reach 2, I've got a radius of 1 and a semicircle. So pi over 2 is the answer to g of 2. What you want to realize is while I sit here at x equals 2 for the g of x function, my value is positive pi over 2. So as I move forward from there, I am subtracting from pi over 2, but I'm subtracting from pi over 2. I'm positive. And if I go all the way over to g of 3, g of 3 is looking at what is the integral from 0 to 3. And I can take where I left off at pi over 2 and then subtract all the area I would be getting. The radius is 1/2. So pi r squared, and then divided by 2, I'm going to get a pi over 8. I want you to take a good look at that and realize that g of 3 is positive. Now, g increases from 0 to 2. G decreases from 2 to 3. But g of x is positive the whole time when x is bigger than 0. Because I'm starting at 0 and I'm adding, making it bigger, 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 bigger. And then I'm subtracting from that big amount, but I never subtract enough to counteract how much I added. So I am actually positive over that entire interval for my g of x function. Now, when I head backward, I need to be a little bit careful. My G is a value of 0 right there. One thing I can do is I can think, before I hit G of 0, I had to subtract numbers to get down to 0. If I had to subtract numbers to get down to 0, I had a positive value. So another way to look at it also would be to flat out just say, all right, what is G of negative 2? G of negative 2 is the integral from 0 to negative 2, which is the wrong order. So if I negate and swap, now I'm going in the proper order, and I get negative whatever the integral says I should get from proper order negative 2 to 0. And the integral says, well, you gave me a negative height, so I'm giving you a negative answer to multiplication. Okay. 5 minutes left, so I need to get you to the quiz. What you actually need to realize is that you have a positive pi over 2 when you are at this G value. And that literally, when you go all the way back to here, you actually are taking away a pi over 8 to get back that far. G of negative 2 is, is pi over 2. G of negative 3 is pi over 2 minus pi over 8, which is still a positive number. So I wanted to emphasize that with you. And I was going to do another one, but we have run out of time. So